All right. So yeah, welcome and welcome to the last talk of the day. And this is going to be by Tran and Julien Tranchida on multi-fidelity and parallel machine learning approaches for combining first principles calculations and classical molecular dynamics predictions. So Tran is currently a LTE senior member of technical staff in optimization and uncertainty quantification, Sandia National Laboratories, Albuquerque, New Mexico. He obtained his BS, MS, and PhD in mechanical engineering from Georgia Institute of Technology in 2011 and 2018, and an MS in applied mathematics from Georgia Southern University in 2014. His current research interests are optimization, uncertainty quantification, machine learning methodology, and applications for multi-scale computational material science. And Julien Tranchida is a research scientist in the computational multi-scale department at Sandia National Laboratories. After completing his doctorate in the French Atomic Energy Commission (CEA), he joined Sandia as a CEA NNSA postdoctoral fellow in 2017 before transitioning to a staff position in 2019. Julien implemented and maintains the SPI and spin package of lamps and works on development of interatomic potentials following machine learning approaches. So this is going to be a talk by both of the speakers, and I will let both of you coordinate among yourself the combined talk. Yeah.
Don't worry, we have a plan.
All right. Perfect. Yeah. Okay then.
um,
Yeah. Please take it away.
so I'll let you share, Anne, as we said yesterday.
Sure. Give me a second. Let me know if you can see my screen. Let's see. Can you see?
Yeah, it seems to be working.
Okay.
Great. Thanks, Anne. Okay, perfect. So thank you very much for the introduction. Just a quick precision. I just moved back to France. I was working as a research scientist at Sandia, and I now work at the Atomic Energy Commission in France. It's just a very recent thing, 1 month ago, but I just wanted to precise that. Okay, so hi everyone. So today, Anne and I are going to be presenting some work we did last year at Sandia National Laboratories. The work is titled Multi-fidelity Gaussian Process and Bayesian Optimization for Materials Design, Application to Ternary Random Alloy. On the bottom right, you can see the reference to a manuscript that is detailing some of the calculations we're going to be presenting today. Actually, there are more calculations in the paper than what we're going to be presenting today, but if you want to have an overview, that's where you can find it. And yeah, that's about all I wanted to say here. Anne, can you switch to the... Thanks. Yeah, is it fine?
Yeah,
okay. We can see the next slide.
Yeah, thanks, Anne. So first, I wanted to give you a couple of slides on the problem we are trying to solve here, kind of like an introduction. So the work we wanted to achieve here was to perform simulation of high entropy alloys. So you probably all know high entropy alloys. Those are metallic alloys, random alloys with 4 or more principal components. They are very promising materials for a lot of applications. Typically, refractory materials or nuclear degradation resistant materials is what was targeted at Sandia mainly for obvious reasons. And at Sandia, there are ways of manufacturing HEAs, new experiments aiming at manufacturing HEAs with additive manufacturing techniques. And so those people, they basically need tools to represent like compute properties of HEAs. And that's related to the thing I'm going to say on the right now. So yeah, so this problem can be seen both as a material design problem and as a machine learning problem. So first, material design can be seen as is written as an inverse problem in the structural relationship, in the structural property, relationship. So what do I mean by that? we mean that for those kind of alloys, typically what you're trying to achieve is tweak the composition over a vast composition space to try to optimize some properties. So that's basically very often the goals. And the composition spaces can be, of course, as you can imagine, very vast. So here we're going to be focusing on a rather simple composition, only 3 elements: aluminum, niobium, titanium. But ideally, we wanted to apply the approach to more complex compositions. And yeah, you can go to the next slide, Anne. So yeah, but it can also be seen as a machine learning problem. So of course you could imagine trying to brute force the problem and run a lot of DFT calculations. That will be rather high accuracy. Well, DFT or another first principles method, another high accuracy first principles method. Of course, as you can imagine, this is also limited by the computational cost. So here we're going to be working on rather simple properties. So it could be, it is possible in principle, but for more complicated properties, you may need, for example, very large cells or other things, and you may not be able to apply that methodology, that brute force methodology. So people are working more and more on machine learning interatomic potentials to try to solve those issues. So try to preserve as much of the accuracy of first principles methods, but with classical potentials, enabling to run much quicker calculations, scaling as n mainly on those properties. But what we noticed with Anne is that the use of DFT and machine learning interatomic potentials is mainly remaining what we would say segregated. So on one hand, you use DFT to create a training data set, and then you use it to train your potential and test it, but then you use your potential independently. And what we wanted to do here is try to fuse the two predictions and try to do useful with that combination kind of, and accurately predict materials properties over for vast composition spaces. Thanks, Anne. Okay, so the first step of the work was to prepare a snap potential, train a snap potential for that ternary random alloy. So to do that, we developed a small framework, it's more like a script basically, that's going to be running classical molecular dynamics with a classical potential with a lot of steps, high temperature, to try to generate a lot of decorrelations between the configurations, spatial decorrelation, I would say, and then apply random colorings and then apply a relaxation to those configurations and put them in a training set. This is a very simple scheme. I agree that more efficient scheme could probably be developed, but that was not really the goal here. We just wanted to have a quick training set with enough decorrelation to start training a potential. Also, another big approximation is that we're going to be focusing on BCC structures. So as you can see on the right, that's basically the data set on the right. We only focusing on BCC structures. Aluminum, niobium, titanium, sorry, I didn't say that, is supposed to be BCC. In practice, when we run all the calculations, we discovered that it's not really, as the experimentalists at Sandia were believing, it's not that BCC. It's kind of like an amorphous phase on a lot of configurations. But anyway, we try to focus on BCC structures. And so as you can see, aluminum and titanium here are in BCC phases, which is not, of course, the actual phases. They're supposed to be FCC and HCP. But again, it's an approximation. Another target material was only composed of BCC elements, and that's why we wanted to get that first step done, basically. So as you can see, the training set is rather large. I mean, you can find much larger training data sets, but it's not small. I mean, especially because all the cells are 54 atoms. So at the end of the day, it's a rather large number of atomic configurations. But it's quite unbalanced too. We have a lot of data at the equicomposition point and not so much outside. So you can't expect having like an amazing potential from that training set. That being said, what we are mainly interested in here is try to understand the correlations between the high fidelity and low fidelity models, and that's why it was kind of like sufficient. Thanks, Anne. We can go to the next slide. And so once we have the data set, we apply that the following coupling between Dakota, which is a software developed at Sandia too, and is actually a developer of Dakota, and is going to show you how to use Dakota for some simulations later in that seminar. So we use that coupling between Snap and Dakota to train the potential. So we basically have a set of hyperparameters to optimize. We have a training set. We have like a Python package that's called FeedSnap that is open source that you can also download. And we basically loop, we compute new bispectrum coefficients, we change the hyperparameters, we compute physical metrics, and we do that with the genetic algorithm of Dakota to try to find the best set of hyperparameters. I mean, at least a good set of hyperparameters, minimizing the energies. So I don't have the number on the top of my head here, but we didn't try to do like an amazing job at developing the snap potential. Again, that's not really the goal of the work here, to get the best snap potential possible. I think we got, if I remember well, I usually try to have, for those kind of studies, I usually try to have mean absolute errors for the energy below 100 MeVs, milli-electron volts, sorry, per atom on average, yeah, MEVs. So not excellent errors, but sufficient for the work we're going to be doing here. Also, I don't use a testing set. I only have a training set here, because it's the snap potentials are rather simple. They don't have tons of parameters, so you shouldn't have a lot of overfitting, and usually, it's not super necessary. I mean, it's not always super necessary to have a testing set in that case. At least that's what I've seen so far. And that's about it. I can go to the next slide. And then, so we're going to be focusing on one property, which is going to be the bulk modulus. So it's basically an entry point work. We wanted to have one quick property that we could compute with both DFT and classical potentials. And the bulk modulus is kind of like the ideal one, because it's already useful to know the bulk modulus of a material as a function of composition, for example, but it's quite simple to compute. So the data here will be high and low fidelity bulk modulus calculations all across this aluminum, niobium, titanium composition space. So we are leveraging two approaches. First, ab initio calculations, as I told you. So in that case, not to build a training set, but to do the actual bulk modulus calculations. So we still use density functional theory as implemented in Quantum Espresso. The calculations, of course, are much lower, but rather accurate. And yeah, that's going to be our high fidelity data. So on the right, you can see typical equation of state we're going to be computing. So it's basically a fluctuation of the energy versus variation of the energy versus fluctuation of the volume of the cell. So all those 6 configurations are at the equicomposition point, sorry. But so we did the same calculation at all the configurations. So the red dots here are the DFT data, and the blue lines are what the snap potential is giving. Because yeah, I didn't say that, but the second level of fidelity is going to be given by classical potential calculations. So we use NUMS. So it's not really molecular dynamics here. We don't run any dynamics. We just compute the energy, basically. So it's basically a classical potential calculation with the snap potential we just developed. Of course, it's much faster. We can do much more evaluations. We can take better averages, but it's still going to be much lower accuracy than the ab initio calculations. And that's going to be a low fidelity data. So basically the blue lines here. And so from the same curves for all the compositions, we're going to be able to do the calculation I'm going to show you on the next slide. So yeah, then we just do fit with the Birch-Mulligan equation of state. So it's this equation of state here. And if you take the second derivative at the minimum of energy of that equation, you end up with the bulk modulus. So that directly gives you basically the bulk modulus of your material. So, and as you can see, you can apply exactly the same calculation for your DFT and MD calculation. And that gives you typical predictions that I'm showing here. So of course, we're doing much less calculations for the high fidelity. First, because it's quite expensive to run them, and second, because it's also the idea of the work to show that with less high fidelity points than low fidelity ones, you can still get an accurate results for the full composition space, kind of. And yes, that's more or less all I wanted to say. Oh no, yeah. So yeah, as you can see, so if you remember well, the training set was that. Yeah, the training set was mainly composed of equi-composition data and data at the niobium, aluminum, and titanium config for those configurations, basically for those compositions. Sorry. And as you can see, that those are the ones we are recovering quite well. And then when you get out of those compositions, well, of course, you're doing much more poorly on the calculation. You have that kind of like on the low fidelity calculation, you have that kind of like red cloud in the middle spreading around, and that's not really what you see on the high fidelity calculation. I'm just going to add one thing. The graduation of the different lines is like from 0 to 54. It's for the same reason as I told you before. It's because we are working with those very convenient 54 atom cells. So for ternary random alloy, it's a very convenient cell, basically. And yeah, that's all I wanted to say for now. And I'm going to hand it over to Anne, who is going to present you some of the theory and the hands-on tutorial. Thank you, Anne.
Sure. Can you hear me okay?
Yeah, perfectly fine.
Okay, great. Yeah, so for me, I work a lot on Gaussian process and Bayesian optimization. So I'm just going to tell you about that. So but before I have a animation of Bayesian optimization process, I think there's a lot of people using that. I think I listened to a couple talks yesterday and then the day before that's mentioned about Gaussian process and Bayesian optimization. I think that's a great tool to use. So just briefly walk you over. So this is the animation that that you have basically. So if you want to try to optimize an unknown function efficiently, so first of all, the Bayesian optimization use Gaussian process as an underlying surrogated model to approximate it, the black box function, which is the one that you want to optimize. So, so in here, I'm just going to show you a very simple example. This is a 1D example. So basically, you're looking for like the point right here that to maximize the function. So the true function is the blue solid line here, and then the dashed line is the Gaussian process, the posterior mean of the Gaussian process, and then the green region is the posterior variant that or proportional to the posterior variance that get you to a 95% confidence interval. So the point is that you want to find this point very efficiently, and so how do we do that? So first of all, so you put in the random point first of all, and then build a Gaussian process on the top of that. So at every single point, it's going to predict a normal distribution, so that you're going to see the mean and the posterior variant. And so one of the question is, how do you find the next point to select and then query and then put it back into the Gaussian process? So they use something called the acquisition function. I think here I put it at utility function, but that's not very precise. So the acquisition function is the function of the posterior mean and the posterior variant. And then the next point is always the point that is maximizing the acquisition function. So the Gaussian process is going to sample at that particular location and then update it, the Gaussian process, and it keep moving forward. And then every time it get a point, feed back into the Gaussian process, update it, refine it. So hopefully, eventually, you have a pretty accurate underlying map or function to approximate. So that's basically the main idea of the Gaussian process. And it is a very versatile and powerful toolbox because it can be extended in so many directions. It can be extended multi-objective, multitask, multi-fidelity, mixed-engineering, scalable for big data, Gaussian process, high-dimensional, synchronous parallel. So in this tutorial, we are going to talk about parallel and multi-fidelities. And you already seen the animation before. So briefly, a little bit introduction about Gaussian process is that if you have a data set that you know, the X is the input and Y is the output. So the prediction is also the Gaussian that we have seen before. And the main reason for that is that it's something very classical from the Bayesian literature, is that the condition of a Gaussian is Gaussian. So when I say that, say for example, you have a blue multivariate normal. If you condition on one particular line and you normalize it, and then again you also have a normal distribution. So a little bit more precise is that if you have a jointly normal distribution like this, and then this is the mean and this is the variance, and then if you condition on this, so it's the prediction will also be a normal distribution. And so if you look at this formula and then compare that to these two formulas, they are very, very similar to each other. So this is a classical result from Bayesian literature. Gaussian process also have kernels. A lot of people mentioned about kernel yesterday. So I just want to briefly touch base on that again, since that the mapping kernel is one of the very popular classes for Gaussian process. And it's basically when you choose the kernel, you make an assumption about the underlying smoothness of the Gaussian process. So the square exponential is the green curve right here is very, very smooth. As opposed to method one is the, or maybe a more precise method 1/2 is that the yellow line here, when you sample from it, it's become very rough. So if you look at the derivative at this particular location, if you have a horizontal line tension here, it's going to be very smooth, and then if it is going to somewhat like have a very sharp slope, it's going to be very rough. So more or less. So using the kernel, basically you make an assumption about the covariant matrix. So you can see K is a covariant matrix, and it's stationary is because it's only depend on the distance between xi and xj's. Xi's and j's are the input of the I and j data point, and because you only make an assumption on the distance, therefore the covariant matrix is symmetric, and then of course positive semi-definite. So to train the Gaussian process, we maximize the log marginal likelihood. So there's 3 terms. So this is the number of data point, and this is the determinant of the covariant matrix, and then you also have to compute the inverse of the covariant matrix. So this is where the computational bottleneck come from. A lot of people treat the hyperparameter as a stochastic variable and then marginalize out using Monte Carlo. But there's also like a very popular approach is just using a deterministic optimization, try to feed the Gaussian process. And as you have more and more data point, this is the cost complexity to scale to train a Gaussian process. So it's typically for the classical Gaussian process, it couldn't scale beyond 10,000 data point. So so more about Bayesian optimization. So anything can optimize. So if you have a very high dimensional space, you can also use random sort. That's work fine too. So, but the point about optimization is about efficiency. So when we try to write optimization paper, we try to argue that this method is more efficient than the other method. So that's the whole point of optimization. So Bayesian optimization is a gradient free, so that we don't depend on gradient. And next input parameter are found by maximizing the acquisition function, which is the function of posterior mean and posterior variance that we have talked about before. So it is also an active learning machine approach because it's balanced the exploration versus exploitation. So therefore, as a result, the number of data that required to minimize is become very minimal. So that's why it's called active learning. So just briefly mention about several acquisition function out there. This line of research is as old as my father maybe, but yeah, people have tried to done research on acquisition function as soon as 1975, and they improve upon that. So this is one of the most modern acquisition functions. It's called upper confidence bound. So in the context of maximization, so in a minimization setting, you will have to flip again and then become a lower confidence bound. But that's something pretty trivial. So as I said before, so the acquisition function is the function of posterior mean and posterior variance, and then fx best here is that the best so far observation that we have. And then if you are interested, you can also go back, trace to the literature and see the work have been done before. So this is related to the upper confidence bound. They are very interesting. And the capital feeder right here is the normal cumulative distribution function of the standard normal function. So, so finally about multi-fidelity. So multi-fidelity is a very interesting approach. So there's a lot of literature right here. One of the seminal paper is from Kennedy and O'Hagan in 2000, where they actually show that you can actually accelerate it, the process using low fidelity. So you have high fidelity, but it's very accurate, but it's too computationally expensive. The point of the paper is to show that you can actually achieve the same amount of accuracy in a short amount of time using low fidelity, or more precisely, the correlation between low fidelity and high fidelity. And this is based on the autoregressive formulation, is that they assume that the high function is rho times the low fidelity function plus some bias. So for a starting point, I would probably assume that rho equal to 1, and then view the low fidelity as a Gaussian process, and the bias also as another Gaussian process. And as you all know, normal plus normal is also a normal distribution. So then you have a very crude multi-fidelity at your hand. And so if you have a covariant matrix like this becomes like a block structure. So if you look at the top left corners become a low fidelity. If you look at the bottom right, this is the high fidelity, and if you look at the corners, is the correlation between high and low fidelity, and the posterior mean and posterior variance is going to calculate exactly the same way in a classical Gaussian process. And we also train using the log measurement of likelihood exactly the same way that we use in a classical Gaussian process. So one of the question about multi-fidelity Bayesian optimization is that, say suppose you already have an input, but what fidelity level that you're going to query? Are you going to query low, or are you going to query high, or somewhere in the middle? So we need a criteria for that. And so our criteria is that we're going to pick level of fidelity T can be like low or high in bi-fidelity setting, or it can be 1 to S like in multi-fidelity setting. But basically we are looking at the minimum trade between the cost cities is the cost to query that simulation at particular fidelity level, and then this is so-called integrated mean square error. We use this quantity as the measure to see how much uncertainty is reduced if we query that particular point. So as an illustration for multi-fidelity Gaussian process, I also put a figure here. I think this is figure 1 from this particular paper. So basically, this is a very common function, numerical function that used to test the multi-fidelity framework. So you have a low fidelity is like this, and then high fidelity, you have a few more points. So this is the true function that you want to approximate it. So if you only feed a Gaussian, a classical Gaussian process in the middle, so this is the best they can do with 4 points. But if you also use the low fidelity level and then train the multi-fidelity Gaussian process, you will see like a huge improvement in terms of accuracy and prediction. So what's the point? So multi-fidelity casts into the problem of like, multi-scale computational material science. We think that the density function theory is accurate, but it's too computationally expensive. But then molecular dynamics, particularly with machine learning interatomic potential, is less less computationally expensive, or more like cheaper, much cheaper. But then the accuracy is just not very firm. So we would like to back it off, support the prediction of this using a multi-fidelity framework to combine the prediction between the machine learning, molecular dynamic, and the density functional theory. So this is a very classical picture from Dirt Brabant. So there's a lot of computational material science application out there. You can look at this from DFT, molecular dynamics, dissociation dynamics, and then crystal plasticity all the way into finite element. So if you look at this, so you can see like the more, so as you go, like this is the classical time length scale picture. So if you go further more and more, so you can say that the fidelities increase, and then this is low fidelity, this is high fidelity. So there's a whole paradigm of fidelity that you can go about it. So yeah. So this is one of our result for the paper. So for I'm just going to show you the picture. Hopefully it show. Yeah, so we start off at 2 points that we have low and high fidelity at this point, and then you see the map changing throughout the time. So that basically is the multi-fidelity Gaussian process prediction as far as this goes. So we start 2 point here, and then adding the third point here, and then finally it's going to the point that we want it to be. And this is low fidelities, so it's like black few circle, and then this is high fidelities, the green square. And we also denoted the vessel for high fidelity is as a star. And you can see like it's mature pretty fast, so it's only sample 1, 2, 3, and then 4. And then for the rest, it's mostly low fidelity. And after it's find the optimum point, it will just go around and refine our other function. So yeah, so this gift is rather long. So if you are interested, we also have a open public Git tutorial right here. So I'm going to copy and paste into the Slack channel as well. So you can see like we also put a GIF out here, and then for the hands-on tutorial, we are going to use the Coda to do this. Yeah, so for the decoder part, unfortunately, we haven't implemented the multi-fidelity Gaussian process yet, but we do have a parallel Bayesian optimization available to be used. So I would just want to touch a little bit on the parallel optimization and why is it a good choice. So classical Bayesian optimization is a sequential approach. So basically you have a Gaussian process, for in the next point, and then you run the simulation there, and then you put it back to the Gaussian process. That works, sure. But say suppose that you have a DFT simulation that takes 12 hours long, and it takes 12 hours to refine one point. That's not very efficient. So if you have a very, very big supercomputer to be used, you can query multiple simulation at the same time. So the question that we pose is, how do we actually accelerate it using a lot more computational resources? And this is something have to do with parallel computing. So we look at this from the angle of Amdahlor and diminishing return when you try to parallelize it. So you have a code that can scale up to a number of times. Say, for example, if 95% of the code is parallelizable, you're actually looking at 20% maximum speed up. And the more number of processor you use, the more you are going to approach the asymptotic. So let's say, so make an example. If you have a molecular dynamics simulation that takes 3 hours to finish with 256 processor, it's going to crunch 20 cases in 60 hours. Or using that 60 cases, if you use one processor for one cases, you have 256 cases. So and this is comparable in terms of fixed computational budget. So the question that we pose is that in a period of like longer time, 2.5 days, and then 10 days, the number of data point that you have is 80 in sequential versus 1,000 in parallel. Which one are you actually better? And our argument is that you're actually better off if you want to use parallelization in here. And of course, if you have a lot more computational resources, you can just use in here and then accelerate it further. So it offers 2-layer parallelism. So yeah. So a little bit more into the parallel Bayesian optimization. So this is the batch sequential Bayesian optimization, and then this is asynchronous parallel. So if you look at the batch sequential parallel, so basically this is the batch of 10 workers, and each worker is going to run some simulation that that's busy. Like if you see busy, it's you know, at red, and then it's idle, it's become green. So if you send off the batches and you wait until like the last work of the batch finishes and send another batches, basically you see a lot of idle time here. So the point of asynchronous parallel is better than the batch sequential parallel, is that it's totally minimized the number of idle time. So as soon as the worker finish one simulation, you can just put in another simulation and then make it work again. So that the comparison between asynchronous parallel versus sequential parallel. So here I'll just touch on the code that we use at Sandia is Dakota. Dakota is a flagship code for optimization and uncertainty quantification. Can be compiled using CMake. Unfortunately, I was trying to compile that on the deep node, but I wasn't able to because it's like a lot of third-party library. So I'm just going to say that if you follow this command, it should be able to get you there. So so first of all, let me go back to the repository. Is it a good time for a tutorial?
Yeah, we have time for a tutorial. Yeah, I think. But
Okay.
do you want to have questions right now, or do you want to have it at the end after the tutorial?
Julien, do you have any opinion?
No, that's fine. Yeah, we should have the questions at the end. You should go ahead and do the hands-on.
Yeah, all right, then please feel free to have the tutorial. Yeah.
Sure. Yeah. So in this tutorial, we are going to use the decoder to run the parallel Bayesian optimization. So I already view images in here. Well, of course, you cannot see that because I already put into the gig ignore. That's pretty tricky. If you use the same CMake command, I will post in and they will compile just fine. And then it would just take you there. So this is how it is compiled for decoder. Unfortunately, it's take a while to compile and it require a lot of library. For example, like OpenMPI, GCC, and a bunch like GSL and Python with NumPy. It's fairly standard, but it's pretty comprehensive. So it will take a while to compile. But in exchange, you have a pretty good code for UQ and optimization in your hand. So yeah. So this is particular example. I'm going to use a Python code that. So if you look at this particular folder based off sequential demos, so we are going to do two demo, the sequential based optimization and parallel optimization, and we have a Python pseudocode here. So basically, let me just open here. So oops. So basically, this is the input. So this is the Python decoder interface that you see. So basically, it will take the input and then look it up from this particular input table, and then this is the output. So this is served as a pseudo simulation. So you have an input, and then you wonder what the output is. So it will be like a lookup table, and we also have, this is a constraint optimization problem because the number of atoms have to be, so we specify the number of simulation atoms in the simulation cell to be less than 54. So anything beyond 54 is constrained, it's not viable. You can think of this analogously as the sum of the chemical composition have to be less than 100. You cannot have more than 100 chemical composition, right? So the way that we do is that we put the constraint here. Constraint negative, it means that it is satisfied, and constraint positive, it means not satisfied. So we'll take, so this is two-dimensional problem.
Anne?
Yes.
Do you mind if I briefly link to the physics part here, just very quickly?
Sure.
Yeah. So what Anne is detailing here, so input and output, basically input.hf will be the composition of the point on your composition space. So you will give the number of, let's say, aluminum and niobium atom. And of course, what Anne was describing here is that the number of titanium is just 54 minus those two numbers. And the output here is the equivalent bulk modulus. And the reason why Anne is saying that it's a pseudo simulation is because in principle, if you wanted to run the Bayesian optimization, you will have to run, for a given composition, you will have to run the actual DFT. Here, we are simplifying the problem because we wanted to have something kind of like standalone that you can run. And so we already, all the bulk modulus values are already computed, but that's kind of the idea. Sorry, Anne.
Yeah, very good, very good. Totally agree. Yeah. So this is the Python script that we have. So basically, it will return two things. So first of all, the output, and second is the constraint. So from here, we also have a decoder input file. So if you look at this particular input file, looks something like this. So this is where the result going to be. It's going to be in this particular file, and this is the initial number of point that you have. For now, we will going to disable this command as this is for parallel optimization, and you specify the lower bound and upper bound for the problem, and then this is interface between the decoder and Python, and you tell that this is the one objective function. You only have one objective, and then also one constraint, which is the constraint that Julien have described. So how do you actually run it? There's a bash script in here called run.shell. So basically just as simple as it is, can be sh run.sh. So just keep running this. So it will tell you, it will update it along the way, tell you what input composition is, and then what is the output going to be. And I also put a random wait function here. This is the pseudo waiting time to be anywhere that you want. If you want it to be like 5-10 seconds, that's fine. If you want to make it like look like DFT function, you can wait for 12 hours. That give you a perfect sense of how expensive it's going to be. But yeah, so if you run this particular file, it's going to give you a result hopefully shortly, and we're going to return to this particular folder later. So for parallel optimization, so I also have a pretty similar directory in the same GitHub folder that you also see the code input file. But if you compare this particular input file in here to the previous one, you see that that in this particular case that we actually enable the batch size, and we do have a different approach for the batches. Say for batch 4, we have 2 points for exploration and then 2 points for acquisition function. So that's this strategy that we use to build a batch more or less. And the argument is that let's say, for example, you have batch size 4, the conversion rate is going to speed up as the square root of the batch. So you have a batch size 4, the conversion rate is going to be double. And if you have a batch size of 9, the conversion rate is going to be triple compared to the classical Bayesian optimization. So we want to take an advantage of this on the high performance computing cluster. And this is how we do it. Oh, one more thing. If you look at this run the sh files, a little bit different because now you have to enable MPI. For each particular worker, it's going to assign a different job. So run a Python on different core processor. If you run the core on MPI, you see that three file at the beginning, three are running simultaneously, and then after this three file return, you can see like it will run like simultaneously at the same time, so that you can have like multiple worker working in parallel manner. So yeah, so any questions so far?
It seems there's one question by Ganesh Sivaraman,
Sure.
and that's in chat. And
Sure.
basically, could you comment on the limit of, or Ganesh, do you want to ask it directly?
Sure, yeah.
Yeah, so I was just wondering, like, what is the limit of the optimization, the dimension of the problem that you can solve? So in terms of like, if you can also compare like Bayesian optimization, genetic algorithm, and then also like Monte Carlo tree search.
Sure, that's a very interesting point to bring it up. Gaussian process. So we talk about dimensionality. So you have to point out the Gaussian process. Gaussian process is particularly good for dimension less than 50 or 20. If so, I must say, for high dimensional problem, it is actually not a very good approach because then you again have a curse of dimensionality, right? Then you have so many hyperparameter that you cannot optimize. So there's a lot of approach to go about that. Like you can also reduce the dimensionality beforehand using like linear dimensional reduction framework, for example, like active subspace or like PCA or any SVD based approach to actually reduce the dimensionalities. Or you can also use autoencoder, like which is a nonlinear dimensional reduction framework. So yeah, but yeah, for Monte Carlo, it's dimensionality independent, so it really doesn't depend on the dimensionality. So yeah, I think that's a good point to bring it up. So totally agree.
Is there any other question at this stage, or do you want to continue with the tutorial? All right, I think we can just continue in that case.
Sure. Yeah. So if you look at the result, you can see that the best. So I'm going to give you like a short summary, more or less, and tell you, okay, you find the optimal point at this particular configuration, and this is the functional evaluation, and yeah, so this is for sequential. For parallel, I think is the result is a little bit better. But yeah, so basically we can obtain the same point that like that we have talked about for the optimal chemical composition. And yeah, it's going to take a while for parallel run to finish. So let's take a look at one of the summary file that the coder get off. So basically, it's going to summarize what is the x1 and x2 that you have, and then if you look at a Python script, there's actually a router operation here that so you cannot have 12.5 atom, of course. So yeah, so going to look at that, going to give you objective function, and then also the constraint that you have associated with this, where the constraint is defined right here. We're going to talk about. So yeah, so it's simply work. So just want to demonstrate and verify that actually the approach is correctly implemented. Yeah.
Right.
You want to switch back to the slides?
Sure.
Yeah, as Anne was explaining, unfortunately, we couldn't really demonstrate the multi-fidelity aspect of the work here. We only talked about the Bayesian optimization. But if you have any question about that, do not hesitate to ask us in the chat or after that. And can you go to the final slide, Anne?
Sure, like this one.
Yeah, exactly. Yeah, so this is the Bayesian optimization, but with the multi-fidelity calculation. But as you can see, we can. So here, of course, you're going to say, yeah, I mean, the result was really obvious. Like we knew because we could do a lot of because basically we also applied the brute force approach and did all the calculations with DFT. So we knew that niobium had the better bulk modulus here. But you have to imagine that you could be able to rerun the calculation without knowing that in advance and greatly reducing the amount of high fidelity evaluations that you have to do, that you have to perform. And that's the direction Anne and I would like to go if we can in the future. So ideally work on more complex composition spaces. So maybe, for example, 4-component alloys or 5-component alloys, and ideally move to 2 properties too. That's something we would really like to do. So try to find the best optimum between 2 properties. And yeah, another perspective on the things we wanted to work on. So yeah, we would be we were considering trying to add a 3rd level of fidelity with much less points, which would have been a higher level of fidelity, and that would have been few experimental points for a composition, because some physicists were also measuring actual properties, the same materials properties for some of the composition points, basically, for some more complicated alloys. And that's something we could have been doing too. And that was, I think, great perspectives that I wanted to share with you all. And with that, I think if any of you have questions, we can try to answer some of them.
So do we have questions here? Edgar, do you have a question?
As Anne said, so you can find all the material on the GitHub repository to rerun some of the Bayesian optimization Anne has been showing you with Dakota. You have the slides, and you also have the manuscript detailing all those calculations on the GitHub repository. And yeah, the link to the GitHub repository was basically on the slides.
Yep.
So I had a question regarding.
Sure.
Yeah. So that's for Julien. So you're saying that your models have errors of the order of 100 MeV per atom.
Yeah.
But is this higher just because, I mean, you're exploring configurations at really high temperatures? Or I mean, what is the standard deviation of energies in your data set per atom energies? Do you recall that? Or
no, I do not actually. I do not remember exactly. To be honest, I don't remember exactly. I don't have the results with me right now, but I would say I probably optimized my snap potential up to that level of average error.
Right.
And,
so but you could have gone below.
Sorry, go ahead.
So you could have gone below that. Is that
yeah, definitely. Okay. Like running my genetic algorithm for longer, also building a better training set, I would say. And yeah, a couple of other tricks we could have been using to get a snap potential that would have been reproducing DFT more accurately.
Okay. And the lack of a test set in your case, I mean, that could, I mean, I'm sure that works for what you're studying, but in terms of transferability of a potential, it could have some implications there, right?
Yeah, of course. So that's something we are very much aware of. I would say if I was doing neural network potentials, I would never do what I did, like to not have a testing set, sorry. But here, because the potential is a linear model, I think the chances that, and you have some papers actually showing that. If you look at some papers, so like one of our coworkers with Anne, his name is Aidan Thompson. He's the developer of the snap potential. He's been publishing a paper recently with Ralph Drautz. And so they show that the transferability of, let's say, simpler potentials is less affected by basically the
yeah, I mean, makes sense. You don't overfit. I mean, you don't have, yeah.
Exactly.
You're less likely to.
Exactly. That's exactly the point.
Thank you.
So that's why I was not too afraid about that. But in principle, you're right. I should do it. If I wanted to, if I really wanted to have an accurate potential for those compositions, I should definitely test that too.
Okay. All right. Any other question, or shall we finish this session? So I think with this, we are at the end of the session, and I'll stop recording with that.